Welcome back. Today we're getting into a really powerful explainer for anyone working with environmental data. We're going to build an automated, multi-decadal geospatial pipeline right from scratch using Google Earth Engine and Python. If you've ever found yourself totally drowning in satellite imagery, trying to stitch together decades of data for an ecological model, well, you are in exactly the right place. Okay, let's dive into this, because this quote right here perfectly captures the sheer frustration so many of us feel. We spend all this time dreaming up these incredibly sophisticated machine learning models, but the reality, the real trap is actually the data engineering. If you're manually extracting satellite data, managing cloud masks, and fighting with weird sensor formats, you know exactly what I mean. As Dr. Faisal Qasim points out, it's at this very stage where projects just completely fall apart. So here is our roadmap for this explainer to cure those data headaches. Number 1, the data engineering trap. 2, a modular geospatial architecture. 3, taming Landsat and water. 4, climate, thermal, and stress. 5, generating ML-ready tables. And 6, quality control and reproducibility.
Section 1. The data engineering trap. Manual extraction fails.
To really appreciate the solution, we kind of have to set the stage by looking at the core problem. Imagine trying to manage hundreds, maybe thousands of spatial units across multiple sensors and climate products manually. It is just a recipe for disaster. When you manually collect these variables, you inevitably make inconsistent processing decisions. Like, did you use the exact same cloud threshold for 2005 as you did for 2020? Probably not. Missing values don't get tracked properly, unintended data leakage creeps in, and your final data set becomes virtually impossible to reproduce or audit.
Section 2. A modular geospatial architecture. Geospatial pipelines.
And this brilliantly illustrates Dr. Qasim's reusable geospatial feature engineering pipeline using Google Earth Engine and Python. You move from pre-processing and masking into feature stacking, and finally into spatial reduction. The absolute genius here is the principle of keeping each transformation modular. By having a sensor-specific pre-processing function return harmonized band names right at step 1, all your later functions just use common names, like green or near for near-infrared. You don't have to repeatedly write code to handle sensor-specific band numbering. It makes the whole architecture incredibly clean. Section 3. Taming Landsat and water. Dynamic masking. So say you're doing a multidecadal study, right? Running from the year 2000 to 2025. You are absolutely going to cross different satellite generations. Landsat 7 uses totally different band mappings than Landsat 8 and 9. Well, the pipeline acts as a universal translator. It takes those wildly different sensor band numbers and converts them into a single common spectral language, meaning band 4 on Landsat 7 and band 5 on Landsat 8, they both just become NIR. Once we have that common language, we have to deal with water. Water creates incredibly misleading vegetation signals. So Dr. Qasim recommends dynamic water masking. This means combining live spectral evidence, like the Normalized Difference Water Index, or NDWI, from your actual Landsat image, with persistent historical layers, like the European Joint Research Center's Global Surface Water Occurrence Layer. To anchor this to real-world impact, we dynamically mask out these deceptive aquatic pixels, so your model doesn't look at a temporarily flooded field and confidently misread it as a dead, deforested patch of land. Now, you've got clean, water-masked optical vegetation indices like NDVI or the normalized burn ratio in hand, you might think you're pretty much done. But satellites actually only tell half the story. We need a broader environmental context if we want to truly understand what's driving the changes we're seeing from space. Section 4. Climate, thermal, and stress. Context layers. Let's define the Continuous Canopy Stress Target, or CSI. Rather than just using raw NDVI, which, let's face it, can be super hard to interpret, CSI creates a standardized anomaly. It measures the departure of the current annual NDVI from a specific historical baseline. Cleverly, the math is set up so that negative NDVI anomalies, meaning less greenness than usual, translate directly into larger positive stress scores for our model. Okay, let's look at the walls of our architect's blueprint, layering in our context data. The model stacks ERA5 land data, which gives us 11-kilometer climate variables like precipitation and vapor pressure deficit, alongside MODIS 1-kilometer daytime thermal data. It also brings in the Hansen forest loss data as an annual event flag. But here's a vital piece of advice. Keep the Hansen forest loss flag mathematically separate from your physiological stress target. By doing that, your model actually gets to learn the relationship between physiological stress and forest loss, instead of just having the answer hard-coded into the math. Section 5, Generating ML-Ready Tables. Spatial reduction. By this point, you have a massive, multi-layered spatial image. The finishing touches here require one golden rule. Avoid exporting every raster pixel. If you try to export raw pixels for decades of data, you will literally crash your system. Instead, we use a spatial reduction stage. Google Earth Engine aggregates the stacked data onto specific geometries, like your sample polygons, and calculates the mean values. Now, what's really interesting about this slide is the resolution column. Dr. Kasim issues a pretty stern warning here about mixed resolution predictors. When you reduce an 11-kilometer ERI5 climate pixel down to a 30-meter Landsat geometry, you haven't magically enhanced the climate data to 30 meters. You've simply resampled it. It is absolutely crucial to remember the native resolution of your source information so you don't end up overinterpreting your final model's localized precision. Section 6, Quality Control and Reproducibility. All right, so these are the crucial final checks required before model fitting to prevent the whole project from just falling apart at the seams. And it starts with data leakage. This happens when a model accidentally uses information from the future or from nearby spatial units, artificially inflating predictive performance. Look, if you're dealing with spatially autocorrelated data where one patch of forest looks exactly like the patch next to it, randomly splitting your dataset into training and testing is going to give you massive false hope. Your model looks like a genius, but it's really just cheating. The fix? Spatial grouped cross-validation. Keep those geographic groups entirely intact. To keep things rigorous, you really want to follow this checklist. Verify your masks. Track your NA values so you spot systematic gaps. Prevent that leakage. Oh, and maintain a processing manifest. I mean, we've all felt the absolute cold dread of blindly starting huge numbers of server exports, walking away and coming back months later with zero memory of what cloud threshold or dataset version we actually used. A simple manifest saves you from that entire nightmare. It's also really important to remember that while this pipeline architecture is totally reusable, your specific parameters must always be calibrated for your unique study system. Like if you're using an empirical equation to calculate leaf area index, you can't just borrow an equation tuned for a tropical rainforest and blindly apply it to a semi-arid savanna. It just doesn't work that way. And that brings us to the end of this framework. We've gone from raw, chaotic satellite bands to a beautiful, reproducible, machine learning-ready table. But I want to leave you with a provocative question as you head back to your own data engineering workflows. Look at your current methods and ask yourself, is your spatial validation actually preventing data leakage, or is it just hiding it? Think about it. Thank you for joining me for this explainer, and keep building those robust data pipelines.